Hi everyone, got a short video here about impulse and momentum and center of mass. So momentum, remember, is symbolized by small p. We have p equals mv. That's the formula for momentum. And so that'd be units of kilograms times meters per second. Nothing special about that. It's basically defined as the equation. So it's hard to really put in words what it is, but the big thing is how to change momentum. So obviously using an equation, P equals mv, is not difficult. So how the momentum of an object is changed is by applying a force and the amount of change you get depends not only on the force, but the amount of time it's applied for. So remember that the change in momentum is equal to the force times the time it's applied for, delta t. Okay? The right-hand side is what we call the impulse. Also remember that the left-hand side can be written in several different ways. You can write it as delta p. You could write it as m delta v. Sorry, that m turned out pretty poorly. You could have m vf minus mvi. All sorts of different ways to write that, but that's the big idea. So this is where things get interesting, is when the momentum of an object changes. So remember, we saw many examples of where you could accomplish the same change in momentum with different forces and different times. Okay. Another thing is impulse on a graph. Graphs tend to be pretty important. So we have force versus time. You have to be really careful, because in the last video we talked about work, and work being on a force versus position graph. This is a force versus time graph, so you have to be very careful if you see one of these graphs, what is on the x-axis here. But if you have impulse on a graph, something like that, then we know that the impulse is equal to the area. So the impulse is equal to the area of the graph there. So that's a pretty straightforward thing. Hopefully it's just reminding you of something that you already knew. So the next slide, we're talking about conservation of momentum. And we need to talk about systems again, because we need to decide whether we have internal or external forces. So for momentum problems, almost always, I can't think of a time where it's not true, you are going to have two objects in the system. And it's usually only two objects. The conservation of momentum can apply to a system with any number of objects, but obviously as you increase the number of objects, it's the same physics, it's just a lot more math keeping track of. So if you can do it for two, that's good enough. Okay, and so the idea is there are different ways of stating the law of conservation of momentum, but the big idea is that external forces can change the momentum of the system, internal forces cannot. Okay, so you may say, I probably put it in your notes, something like, let's see, for a closed system, the momentum of the system remains unchanged. You can say it that way. Other things, but that's the idea. Internal forces cannot change the momentum of the system. The external forces can. So let's imagine curling. Okay, so this is the curling stone, and so this is number 2, and let's say that V2 is equal to 0. Okay, and this is stone number 1, and suppose that somebody is pushing that with an external force. So there is this force F. Okay, And that is coming from, let me see if I can draw this here. I'm drawing a person. They kind of kneel on there. So what do? They kind of do that, and they push on there. Okay, so with that force F. Okay, so the question is that an internal or an external force? Well, the system, we're going to consider the system be the two stones, stone 1 and stone 2. So since F is exerted on stone 1 by the person, that's an external force. And an external force is going to change the momentum of the system. So we can see this one's going to remain constant speed. This one is going to speed up because of that force. So the system momentum is increasing. So this would be a good time to do a calculation of, how long was that force applied for? What was the initial velocity? What would be the final velocity of stone 1? Okay, but eventually the stones reach each other and they collide. So stone 1 and stone 2. So there is a force on stone 2 by stone 1. There is a force on stone 1 by stone 2. So the question is, are those internal external forces? The objects are going to, the momentum of each object is going to change because there's a force there, but what about the momentum of the system? So these are internal forces because it's one object in the system pushing or pulling on another object in the system. So that means we have internal forces. And that means the momentum of the system remains unchanged. So what we can say is here we usually have a before and an after or something. So before the collision, we had M1 and V1 and M2 and V2. So that would be the momentum of the system before the collision. And then after the collision, each one would have a momentum mv, but it's a new v, so we usually use a prime there, plus m2 v2 prime. Okay, and so that equation is useful in most of the problems that we do. So once you know that momentum is conserved, you can use that equation to solve that. Okay, now collisions, there are three types of collisions. Okay, and elastic collisions, remember, are very special. So in elastic collisions, the objects bounce off each other, and to call it elastic, what has to be true, remember, is that the kinetic energy must also be conserved. So anytime you have a question where they ask, is this collision elastic? Okay, you can't just say they bounce off each other, so it has to be elastic. You have to check that kinetic energy. Find the kinetic energy of 1 and 2 before the collision, add them together, see if you get the same answer for the kinetic energy of 1 and 2 after. Okay, inelastic is usually we are talking about where they stay together. Although technically, since elastic is only this case, there are things where they bounce off each other, but they're not elastic. Actually, they don't fit that kinetic energy thing, so people call those partially elastic. Some people would still call them inelastic, but inelastic, we usually deal with the extremes. And then the recoil example is not really a collision, but that's when the objects are together. And then separate. Okay, so that's, people on roller skates pushing off each other, a gun being fired, the bullet goes one way, the gun recoils in the other way, cannon, all sorts of different examples. Sometimes they're moving initially, and then they recoil, and that still works. But the most common way is that they're at rest to begin with. Okay, and then we have the idea of center of mass. So remember the center of mass of the system. Okay, if we have two masses, equal masses, they're both m, the center of mass of that system will be right there in the middle. Okay, usually use COM for center of mass. If one mass is larger than the other, big M and little m, the center of mass will be kind of like a weighted average, so it's going to be much closer to big M. Okay, and the center of mass, there are certain times where the idea of center of mass is really useful in helping you solve a problem and explain what's going on. Okay, and the big idea with center of mass is that only external forces can change the motion of the center of mass of a system. Okay, so only external forces can change the motion of the center of mass of a system. So if you have a system of these two blocks, for example, and let's say that they are a spring, and let's say this is sort of a top view, and they're on an air table or something like that, like air hockey, so there's no friction here at all. Okay, and then let's say that these are given a push so that they have a velocity v. Okay, and so we have they are connected by two masses attached to a spring. And there's some sort of remote trigger system here. So that at any time, so right now they're traveling this way at this velocity, and then at this point the trigger is pushed and the spring is going to push on both objects. So the force is going to be upward, but they still have inertia in the sideways direction, which means that the velocity is going to be in that direction and in that direction. Okay, so they're going to travel that way apart from each other. But the thing we want to pay attention to, that center of mass, will be right there in the middle. Okay, so at this point, this is where the center of mass would be. And it would still have that same, let me call this 1 and 2. So this would be V1 and V2. These two V's are not necessarily the same as that. But the velocity of the center of mass would still be equal to that original V. This V equals that V. This V equals that V, because internal forces acted on there. So that would continue on. Okay. Another example where you can kind of think in terms of center of mass is if we have these two that are stuck together. Okay, same sort of system. So our initial V is equal to 0, and then later this is triggered, so they haven't moved in space. So this is kind of like before and after. Sometimes I like to do the before side and the after side. So in this one, we're going to have a velocity v, we're going to have another velocity v, and the center of mass, again, since we had internal forces, the center of mass remains at rest. So the velocity of the center of mass is equal to 0. Okay, as it was before. Again, so internal forces, they are not changing the velocity of the center of mass of the system. Our third case is the similar setup, except now one of the blocks has much more mass than the other. So let's say that these things are moving along, and so let's say these two have a velocity v, Okay, and then so they are moving along here, and then at some point the trigger was pushed, and so now we have a, if we look at V1 at 1 and 2, so this would be V2, and then this would be V1. Okay, so if we look at this, object 1 was moving to the right with a velocity v. When that trigger is pushed, there's going to be a force to the left. So we know that v1 would be less than v2, the original v. And then at 2, it was moving with velocity v, and then there's a force to the right which would increase its velocity. So v2 would be greater than v. But the center of mass would still have a velocity v. So the velocity of the center of mass would equal v. Okay? So sometimes that can be used to explain things in a much easier way than potentially what they're doing that. The velocity of the center of mass, you're not going to be asked to calculate a numerical value of that, but this is a case where having this model in your head about how that works can really simplify things for you for some questions. All right, that's all I got for this one. Thank you.